Hi, in this lesson I will take forward the example of limit of a function fx as x approaches a. Limit of a function fx as x approaches a. To explain precisely the concept of limit, and I will introduce the formal definition of limit. We discussed the case of a stone dropped from a height at time t is equal to 0. The distance travelled by the stone from the point where it was dropped is given as s bracket t is equal to 5t square. S bracket t is a familiar notation as used in f bracket x, which shows that s, the distance from the point where it was dropped, is a function of time. Let us find the average speed of the stone for the period of delta t seconds lasting from t is equal to 3 seconds to t is equal to 3 plus delta t seconds. I want the average speed between two instances. First instance is time is equal to 3 seconds and the second instance is some time later. How much later? I denote that additional time by delta t. So delta t later, which means the time now, is 3 plus delta t seconds, and the duration of this interval is delta t. Using this formula, s at 3 seconds is equal to 45 meters and s at 3 plus delta t seconds, 5 into 3 plus delta t whole square. Let us expand this. 3 plus delta t whole square works out to 45 plus 30 into delta t plus 5 delta t square. The distance travelled during this period of delta t, the distance travelled, I denote that by delta s, which is the difference between the two distances. The distance travelled is this minus this, which works out to 30 delta t plus 5 delta t square meters. Average speed for the period is delta s, the time travelled, distance travelled divided by the time duration, and if delta t is not 0, I emphasize this, if delta t is 0, 30 into delta t will become 0, 5 into delta t square will become 0, divided by delta t this will become 0, so this will become 0 by 0. So only if delta t is not equal to 0, this can be simplified as 30 plus 5 delta t meters per second. Notice this is a function of delta t. The average speed of the stone from t is equal to 3 seconds to t is equal to 3 plus delta t seconds, which is a period of delta t seconds, is a function of delta t given by this equation. So I can write it as f of delta t is equal to 30 plus 5 delta t, where delta t is the duration of the interval for which I am trying to find out the average velocity, and the duration begins at 3 seconds, which is fixed here, and this 3 seconds results in this number of 30 in my equation. Now I have to choose a value of delta t which should not be 0. Like in the previous case, I had chosen 3 seconds and 4 seconds. Then next example, I had chosen 3 seconds and 3.1 seconds. I can put any value of delta t and I get the average speed for the duration. As you can see, if I reduce the value of delta t, the average speed gets closer to 30. And In fact, there is no limit to how much I can reduce delta t. I cannot make it 0, but in mathematics the beauty is there is no limit to how small I can make. So I can bring the value of this function, which represents the average speed for the duration delta t. I can bring this function as close to 30 as I want. How can I bring it? By reducing the duration for which I am looking for the average speed. This exact thing, the value of this function can be brought as close to 30 as I want by bringing the value of delta t as close to 0 as needed. Notice, as close to 30 as I want. That means there is no lower limit. I can choose any number as close to 30 as I want, and correspondingly I will find out a number for the delta t, a duration as small as needed, so that I can get the function average velocity as close to 30 meters per second as desired. This is written as limit of this function as delta t approaches 0. And this exactly happens to be the definition of instantaneous velocity. How else do you define instantaneous velocity or instantaneous speed? Velocity or speed is defined as the distance traveled during a given interval divided by the interval. Then how can you bring in the word instantaneous? The word instantaneous implies limit of this average velocity as the interval becomes closer and closer to 0. So what we have got here is limit of this function as delta t tends to 0 is equal to 30 meters per second. With this clarification, with this repetition of the example that we have done already, we are now ready for a formal definition of limit of a function. Formal definition for the limit of a function. For a function fx, which is a function of x, if for every epsilon, howsoever small but not 0, there exists a delta which is greater than 0, not 0, such that whenever absolute value of x minus a is less than delta, fx minus L, absolute value of fx minus L is less than epsilon. If this condition holds, then L is said to be the limit of function fx as x approaches a, and it is denoted by, it is written in mathematical language as L is equal to limit of fx as x approaches a. As with most mathematical definitions, this one is also very accurate, precise and definite, but at the same time rather difficult to read and comprehend. So let us try and break it down to more understandable language. For a function fx, we want to define the limit of fx as x approaches a, as x approaches a. For explanation, I will draw a line which represents value of x and a is here, and I will draw a line which represents value of fx, and on this line L occurs here. I am given a target. I want fx to be in the vicinity of L. Vicinity, how do I define the vicinity? In a vicinity which is deviating from L not more than plus epsilon or minus epsilon on either side. Epsilon is used to denote some small quantities. So I am given a band, and the target objective is to keep the value of fx within this band of plus epsilon or minus epsilon of L on either side, by keeping the value of x close to a. And This can be achieved by ensuring that value of x remains in the vicinity of a within a band of a plus delta or a minus delta within this band. Whenever value of x is within this band, a plus delta up to a minus delta, but not at x is equal to a. It can be close to a but not exactly at x is equal to a, not necessarily at x is equal to a, but whenever x is in this range but not at a, I can guarantee that fx will be in the range of L plus epsilon minus epsilon, plus minus epsilon. And this is true no matter how small an epsilon is selected to be. I can be given a target to bring fx close to L. How close in a narrow band, how narrow, there is no limit specified to how narrow. I can be asked to bring it as narrow as anyone can imagine, as narrow as mathematics can permit, and I should be able to achieve this by making x reside in a band around a within a plus delta minus delta. The lower the value of epsilon will be given to me, the lower I may have to bring plus delta minus delta, the narrower I may have to bring this band, but it will always be possible, no matter how narrow a band around L I am given as a target, I should be able to get a corresponding band of x which is around a. That means whenever x becomes close to a, fx becomes close to L. If this mathematical condition is satisfied, then L is said to be the limit of fx as x approaches a, and it is written in mathematics as limit of fx as x approaches a is equal to L. I would like to add a small but significant correction here, and I'm glad that it is coming back as a correction because it will also serve to highlight an important point which would have possibly just got overlooked had it been written correctly in the first instance. Revising the definition of limit, the condition is that if I am given a band of plus epsilon minus epsilon around L, I should be able to find a band around A of plus delta minus delta, with the condition being that whenever x is within this band, the value of function fx should remain within this band. However, there is an important exception. Condition is whenever x is within this band but not necessarily at a. X is equal to a is actually exempted from the condition of the limit. To incorporate that in the mathematical definition, I have to bring in x minus a is necessarily greater than 0. Whenever x minus a, absolute value of x minus a is less than delta but necessarily greater than 0. So if at x is equal to a, the condition of fx being within this band is not met, that is still within the definition of the limit.